Okay, similar to my mentor, Steve Mahan, had in this paper I just flashed in front of your eyes, I picked a similar title here, Hybrid Simulation Past and Future. And over the years, I worked in hybrid simulation. I was fortunate enough to work with great people, including Steve Mahan, Selim, Shahzad, Phil, who's sitting in the back here, and several students. Tariq is not with us, but Muhammad is back there, and Alex is somewhere here. And I was also fortunate to have funding from other sources that helped me in doing some work related to hybrid simulation. So I have a few slides, but I will flash some of them quickly because other speakers will elaborate on that throughout the day today, and some of it also tomorrow. But the two main themes that I have picked over the years in work that I do related to hybrid simulation has to do with development and enhancement of the method itself, and then several applications. So I have 6 applications to flash in front of your eyes fairly quickly. And in my role as the director of PEER, as you know, and I'll talk about that a little more during the lunch. So you're going to hear me again during the lunch, but I promise it will be very short, and hopefully it will not make you lose your appetite. And I will focus on talking about PEER and what PEER does. But in a nutshell, we focus on performance-based earthquake engineering. So we try to make use of hybrid simulation in that broader context, and I'll show a couple of slides about that. So as you all know, hybrid simulation has to do with combining analytical simulation, which could be a finite element model as such, and a few components or elements of this analytical simulation may make sense to put them in a laboratory experiment. So there will be experimental simulation of physical modeling. You put the two together, you have some sort of a hybrid system or hybrid simulation. So my first encounter to hybrid simulation is this paper I have written back in '98 that came out from work I did while I was still a student at Cornell. Certainly that's many years after Steve Mahan have done a lot of work already in hybrid simulation. So I was learning from all the work that was done here in Berkeley and Japan and in other places. And we looked at this system that has a 2-story. We were wondering, how do we apply lateral load to this system using actuators? Should we put an inverted triangular loading or equal load at each story? Then I ran into this paper I showed you early on. Oh, there is something called pseudodynamic. Oh, we can do some analysis while we do the experiment and let the loading of these 2 actuators be decided based on a computer model that may be just 2 degree of freedom system, which is something like this. So that's what I'm starting with. And I don't know what's going on here, but something to do with the fonts. But you write your governing equation of motion. Usually these are input to your numerical integrator. Usually these are what you try to compute. And you include some kind of a numerical integrator to integrate these coupled differential equations. But in hybrid simulation, maybe one of those degrees of freedom is a physical model, which is this red spring here. And in that case, you may have a test specimen that may look like this. And then you have the second story as a computer model. Then again, you're still solving the same system of equations, but this restoring force or this force feedback, part of it now is measured and part computed, right? So why do we do hybrid simulation? This work, I took only one example that was part of what Professor Mustafa sitting back there when he was doing his master thesis here in Berkeley. And I see this as a good example. We wanted to test this 500 kilovolt electric switch, and it's too big. So either you make a hole in the ceiling of your shake table building and have somebody pay for it. That may cost several thousand of dollars to be able to test something that big. Or you say, well, I can actually substructure this. I know how to model a support structure, which is just a steel frame, but the switch sitting on top can actually be brought on the table. And then if you manage to analyze this green frame while testing the switch sitting on the table, maybe you need to apply not just translation, but maybe rotation as well. But given you have a 6 degree of freedom shaking table, and we will see a demo about that tomorrow, I think, right?
Yes.
So then you can actually achieve the goal of, instead of having unrealistic dynamic representation of the system by doing only quasi-static test or an expensive shaking table test, you can actually do something in between where you can benefit from these 50 years of development of hybrid simulation that goes back to the early work of Steve Mahan, Masayoshi Nakashima, and others. So that's usually the goal, or one of the goals why we do hybrid. There could be other goals. There could be difficulty in simulating physically the mass, or a very large structure that we cannot test, or something you cannot scale down and put in the table. There could be a variety of reasons, but that's one example why we would do hybrid simulation. So what I will show next is basically 6 applications that I was directly involved in over the years. One of them is related to this motivation I just talked about. When we deal with electric equipment, we have all kinds of electric equipment. If you go to any electric substation, you see many types of these equipment. The class we focused on is some kind of an electric equipment that may be made of porcelain or made of polymer that is hard to simulate analytically, and some steel support structure that's relatively easy to simulate analytically. So then it's a perfect problem for substructuring. Clearly the dynamics of the system is affected by the detail of the analytical model. In this case is the support structure. To be able to conduct a variety of tests on the shaking table of this system will be very costly, time consuming, will be very hard to develop some kind of qualification specs, let's say, unless you have lots of resources, maybe from MTS or from other funding agency. A couple of other reasons is some of these posts are made of polymer, which require paying attention to the rate of loading because they are sensitive to the rate of loading, which mandate doing some kind of real-time hybrid testing. And these are distributed mass. So the idea of just attaching actuators at discrete points may not be very accurate because this has infinite modes of vibration. So you have to do it on a shaking table configuration, and that's probably why MTS has great interest in hybrid simulation, because they are the people who make shaking tables. So if we put these together, then you end up with a body of knowledge that's out there. These are a sequence of 4 papers. I was fortunate enough to work with several people on, mainly Selim Gunay, who will be talking a lot today and tomorrow, where we try to develop a system that can actually focus on testing these kind of electric equipment because the need was there. One of the things that he will talk about is the use of 3 variable control that's developed by MTS. When we wanted to test a variety of equipment that go from flexible to very stiff, so you cannot just control displacement, maybe you have to worry about controlling velocity and acceleration. So we, the early development of this, and it's kind of a good segue of how hybrid systems are put together, is you combine some kind of a data acquisition system with a computational platform, which could be programming your DSP card or having some kind of an interface to MATLAB or some other computational platform. You have a straightforward controller and a little shaking table here that we have on the Berkeley campus. So the first step, you do some computation. You pass the computed displacement, in this case, to your controller. You let your controller do its magic. It goes to the actuator that run the table. You measure the force feedback, and you keep doing that in a loop. The challenge is to be able to do that quickly and efficiently, so maybe 1 millisecond or something, which is your time step where you have to do this loop in a fast way. And there are so many techniques on how to do this fast and efficient. It all depends on how big your computational model is. It could be a single degree of freedom, a discrete system of degrees of freedom, or could be even a continuum. So I'll show you a few examples of that. So if we go back to the problem we have interest in, looking at this 230 kilovolt switch. So this is a test we did on the shaken table a few years ago, but you can take the support structure, put it in SAP or put it in OpenSeas, and you have maybe one of these porcelain insulators sitting on this 1 degree or 1D shaking table, and you make these two talk to each other. You are faced with some delays because your computation cannot be fast enough, so there may be a situation like this. We have done some old work on that, and we developed some feed-forward compensator. There are so many other techniques, but here I'm just showing examples I was involved in. This doesn't mean that's the state of the art. There is great work out there. I'm just taking liberty of showing you things I have done myself. Selim also will talk about some recent work we have done in delay compensation. This was a very simple compensator where the error is related to the velocity of the actuator. It works very well, however, at the peaks here, at peak displacement, where velocity by definition is 0, so you will not have any compensation or feed-forward compensation. So the error will persist, but maybe other techniques can take care of that if this was a problem. Over the years, we have done many validation tests just to gain confidence in these kind of methods. So again, going back to the shake table experiment and its corresponding hybrid simulation version. And if you look at this from far, the top two plots here correspond to the hybrid simulation test, which if MTS is going to invest on that, is going to invest very little. But if they want us to do more shaken table tests, it's going to be more expensive. And it depends how you weigh. If you go back to this first motivation figure, it is the compromise between cost and accuracy. And you may be content with that's good enough if it's done cheaply versus something that's more expensive. One thing that's interesting in these kind of tests is how, because one would say, well, if you are that good in doing simulation, why don't you just do the whole thing as in the computer, right? Which is certainly possible, but when you look at the base of these posts, it's a highly disturbed region. So if our interest is to look at strains at these locations, as we all know, finite element modeling will not be very accurate in these regions if you're looking at the strain level, because that's what's going to trigger the fracture of this porcelain. So if you are looking at this kind of local measurements, you have no way but test these details or these critical regions. So this is great, but now in the bigger context of PEER, where we focus on things that involve performance-based earthquake engineering, where we go all the way from hazard to the loss estimation, where does hybrid simulation fit in this grand scheme of things? So the way we break down the performance-based earthquake engineering framework is to do hazard estimation, to do structural modeling, damage assessment, and then do loss estimation. So hybrid simulation is basically where the structural box comes here. If you don't know how to model something purely in the computer, this is where hybrid simulation can fill in the gap. So then in the larger context of performance-based earthquake engineering, the idea is to go from engineering demand parameters like these are peak displacements or peak strains, versus, let's say, varying the stiffness of the support structure. Why can we do that? Because the support structure is modeled in the computer. So it's very easy to go put braces or put isolation or do whatever. So this is your parameter here that just by varying your computational model. And this could be what you measure, whether it's at the connection that I showed you where you have your strain gauge, or you're measuring the maximum displacement at the top. So here is a mix of engineering demand parameters that come from a hybrid simulation. The idea at the end of the day is to be able to convert that to some kind of expected losses or something of that sort. So this is where you go back and look at where is this equipment. It sits in some kind of a electric substation, that there is a particular hazard of this region. This is a particular substation in San Jose. And you start looking at what lead to losses that this substation may suffer in an event of a magnitude 7 earthquake. So you have two types of losses that may happen. The bus may break because you have lots of deformation happen at the top of the equipment, or you may have fracture that the whole post may break. So you have two kinds of engineering demand parameters. Something related to the strain, because usually the fracture is triggered by exceeding some kind of fracture strain. Or the deformation where the equipment start maybe banging against each other. So that opened the door of even more use of hybrid simulation. So you may be able to model two pieces of equipment with the conductor bus as either a physical specimen or a computational specimen, and you can actually start looking at design parameter that you can tell the designer of this substation how much slack of this conductor cable between the equipment you need. So there is a variety of results you can get, like for intermediate or required or ample slack. You have different type of losses, and you can design your system as such. So I'll go very quickly. Here is an example of using hybrid simulation for a box girder system. That was the work of Professor Mustafa back there on his PhD, when we wanted to look at these kind of systems, and we had to develop a system that make use of the combination of open seas and open fresco, and you will hear more about that, such that this system can be developed and deal with these kind of problems. We also had a study that looked at turbine blades. In a turbine blade, you have the blade and then you have a stiffener. And people were interested to look at the influence of this stiffener in the tearing of the edge of the blade. So this is a perfect problem for hybrid simulation, because basically you can model the blade in a computer, you can use ANSYS or whatever, and just the stiffener is tested on physically, because the stiffener is made of viscoelastic material. Maybe it's not easy, maybe even it's a proprietary that the manufacturer will not give you the properties of this. So, but they are willing to give you a piece to test. So you just put it in a hybrid system, you make it interact with your computational model. You can do similar things. Let me just go quickly here. This is a project we had in China that was looking at the curtain wall of the Shanghai Tower. Shanghai Tower curtain wall system is a very interesting system. It consists of very large glass panels that hung by cables. And if we want to test the safety of this system, we can think of the glass as being simulated in the computer, while the cabling system, similar to the stiffener of the turbine blade, is tested analytically using, tested physically using the same kind of hybrid system. You can also look at the structure insulated panels. That's actually the first example I showed you where we have this 2 degrees of freedom, where this panel is made of a skin with a styrofoam in the middle that may be not suitable for computer modeling, but maybe a 2-story system. The second story is modeled in the computer, the first story is tested in the lab. So we also had this kind of system, and you can vary a variety of things where you study the problem with realistic loading that come from the hybrid simulation. Going back, this is the last example here, going back to this interconnected equipment. Why this is important as a last example, because this substation during earthquakes may suffer something like this, and we can only speculate that one piece of equipment failed and then start pulling on the rest, right? So you need really to study the problem in a holistic way. This is the system we had for NISA at Berkeley a few years ago, and we will hear more about the inclusion of the 3-variable control in the context of hybrid simulation later, because we were interested not only in the high frequency or the low frequency, but somewhere between the two. In this range, because we wanted to test a system like this where you have 2 shaking tables connected by a conductor cable, and underneath each of these equipment you have a different support structure. First, why we need 2 tables? Because the support structures are different. Even if the ground motion is the same, the amplification will be different. And then why some of these equipment are very stiff, some are flexible, so you need a very advanced controller to do that. And you can get interesting results that you can use. Just a few slides about future direction, very quickly. One is the theory. We have done some work on that, where you go back to basics and say, well, what are we really doing? We have a domain that we decompose. Half of it go to the computer, the other half go to the lab. What happened at the interface? So we have been studying this problem, but we haven't gone far enough. So I see a future in this direction. So here is an example of going back to the basics of beam theory, going back to the basis of plate theory, right? And given we have a closed form solution, you can start to look at trajectory of errors. You can start looking at why spurious modes may come in because of this artificial separation. So that's some work we have started, but we still have room for improvement for plates. The same thing where you start seeing vibrations happening, not because of the system, but because of the subsystems. And the mismatch that happen at the interface that is caused by your setup is something that need to be studied. The last example I will show you is how to use hybrid simulation in a multi-physics problem. So here is a project we have that look at energy efficient buildings. So we were interested in developing energy efficient facade. So this doesn't have to do with earthquake engineering or even loading. It has to do with lighting. So there are computers out there that can analyze the amount of light in indoor that we can make use of. But if you have an innovative facade, like translucent concrete or using fiber optic or something like that, you have to test these things physically. So Alex sitting back there will talk to us later tomorrow, right?
Tomorrow.
About how do we mix physical measurements for lighting together with computational modeling of indoor. And he developed a few things in his work where you combine an outdoor device, which could be what we call a cube, which may have this innovative facade, but this is too small to model the indoor light distribution, so he may couple this with some indoor modeling to study a variety of features of the amount of light coming in and then controlling shades or things like that. So in the interest of time, I will just skip this. Just I will mention that this would be your lab in this different physics problem, which will study what happened with light coming through this innovative facade. This TCP here is translucent concrete panel that may be talking to another computational platform, and there is a back and forth communication. Or maybe talking to another lab to study the problem in a holistic way. So because the light has two types, either diffuse light or direct light. So you may study the diffuse light through this system. You may study the direct light through a heliodome system that architects use. So it will be a physical hybrid simulation. My last slide is computational hybrid simulation, something that Andreas worked on, where you can use OpenFresco to connect to two pieces of software, where maybe this model is suitable for MATLAB, while this model is suitable for OpenSeas. So you can study glazing together with steel framing, let's say. So this is my last slide. Is just a few concluding remarks. Hybrid simulation is indeed an economical and accurate testing method that can tackle a variety of problems. Real-time hybrid simulation parametric study can actually be conducted in an efficient way without the need of very expensive tests on a shaking table. The benefits of hybrid simulation can really be seen if hybrid simulation is put in the larger context of performance-based earthquake engineering. Hybrid simulation is a very convenient way to look at a variety of real engineering problems where you can relax constraints of the scale, constraints that we may face if we want to physically model the entire system. There is theoretical foundation that we should look at when it comes to a hybrid simulation. We just scratched the surface, and there is a high potential of hybrid simulation to tackle other type of physics, not just dynamics or not just earthquake loading. So I will stop here, and sorry for going a little over time. And I'll be happy to answer any quick question, or we can leave that to the panel.
We're good on time.
Yeah.
We're good on time, so you can answer. Yeah.
So sorry for going too fast, but you're going to see the details throughout the 2 days, because there will be many presentations that will talk about the time delay. Salim will talk about that. We'll talk about OpenFresco. We'll talk about maybe computational, or maybe OpenFresco Express, or so many other things that I didn't go in depth in. Yes, please.
Are we going to get a copy of all of the slides in electronic form eventually?
Two things. We will, at least from our side, we will post all our presentation online, and within 1 month we are planning to have a peer report that as a minimum will put the hard copy of all the presentation. From the peer side, we have no problem. If there are presentations from MTS that they have some concern in putting in a publication, of course we need to get their approval, or whatever material they don't want to include. We'll be happy to accommodate that. But certainly this set of slides will be available online and also in the peer report.
Also, the videos will be posted.
And the videos will be available.
Yeah. So give us a few weeks afterwards, and we'll compile everything. It'll be all available.
Any other question? But the fact that the slides will be available, I guess that answers all the questions. Okay. Thank you.
Thank you.